Hello everyone. I'm going to present online stochastic matching, Poisson arrivals, and the natural linear program. I'm Xinhai Shu from the University of Hong Kong, and this is a joint work with Zhiyi Huang. Online bipartite matching is mainly motivated by online advertising. Consider a search engine. Advertisers want the search engine to display their ads to the users. When a user performs the search engine needs to select relevant ads and display them to the user. This problem is often modeled as online bipartite matching, which is first studied by Karp, Vazirani, and Vazirani in 1990. In this model, there is a bipartite graph G with two parts, I and J. I is the online part, and J is the offline part. The online part I arrives one by one, and the offline part J is known upfront. When an online vertex arrives, its adjacent edges are revealed to the algorithm. Then, the algorithm needs to make an irrevocable decision on which offline vertex to match. The goal of the algorithm, in the unweighted case, is to maximize the cardinality of the final matching, and in the vertex-weighted case is to maximize the total weight of the matched offline vertices. For example, there are three offline vertices in this instance. When the first online vertex comes, it has two neighbors, and the algorithm chooses the second one to match. Then, the second online vertex has only one neighbor available. Finally, the last online vertex has no neighbor to match. In the end, the algorithm finds a matching of size 2, while the benchmark, which is the optimal solution when all the vertices are online, is 3. So we say that in this instance, the competitive ratio is 2/3. The performance of an algorithm is defined as its competitive ratio in the worst instance and the worst arrival order of the online vertices. So we also call this model the worst case model. The competitive ratio in this worst case model are often considered to be too pessimistic. So researchers introduced some type of stochasticity to improve the result. The weakest form of this stochasticity is called the random order model. It's almost the same. The only difference is that in this model, the online vertices arrive in a random order rather than the worst order. For our topic, the online stochastic matching, introduced by Feldman, Mehta, Mirokni, and Muthukrishnan in 2009. It has a stronger assumption on the online vertices. In this model, there is a random bipartite graph G with also two parts, I and J. There are big lambda online vertices in total. So here, the J, the offline part, is same as before, while I represents the different online types. When each type has its own neighbors in J. When an online vertex arrives, it first draws its online type. This type determines its neighbors. Then, the algorithm makes an irrevocable decision on which offline vertex to match. So this model is parameterized with the arrival rate lambda I of every type I, and the big lambda equal to the sum of all lambda I. So each online vertex draws type I with probability lambda I over big lambda. So this is our topic today. Here, we present some previous results in these three models. In the worst case model, the best result is 1 minus 1 over E in both the unweighted case and the vertex weighted case. And these two ratios are optimal. In the random order model, 0.696 is achieved in the unweighted case and 0.662 in the vertex weighted case. For the online stochastic matching, the previous result has 0.706 in the unweighted case, while in the vertex weighted case, there's no improvement. Our work improved these two results to 0.711 and 0.7009, respectively. Before I present our work, first recall that in the online stochastic matching, the total number of online vertices are fixed, and each online vertex draws its type from a certain distribution. We actually introduced a new model called the Poisson arrival model. The main difference is that in the Poisson arrival model, the total number of online vertices are no longer fixed. Instead, each online type I independently follows a Poisson process with arrival rate lambda I. So here, the big lambda represents the expected number of the total online vertices. This independence is very important in our analysis and the algorithm. Consider a very simple algorithm called independence sampling. So that is, each online vertex independently samples one of its neighbors. So in the Poisson arrival model, to consider the one offline vertex J, the probability that J is matched by each type is independent from each other. So this is the importance of independence here. Given these two models, the first, we need to state that these models are asymptotically equivalent. That is, the competitive ratio in one model also holds in another. If the big lambda is sufficiently large, there are two reasons for this. First is the concentration of Poisson distribution. Given the big lambda, the total number of online vertices lie in a very small range. Second is the monotonicity of the solution. In both the algorithm and the optimal solution, it's natural that the first online vertex is more likely to be matched than the second online vertex, and the second one is more likely than the third one, and so on. This means that the gain in each round is decreasing. So the last online vertices doesn't count very much in the final result. For these two reasons, we can state that these two models are asymptotically equivalent. And it's common in the previous work to introduce an auxiliary LP to bound the optimal solution and help the algorithm and the analysis. Here, we also introduce a natural linear program. The variable xij represents the probability that the edge ij is contained in the optimal solution. So here, there are three constraints. The first one and the third one are trivial, while the second one is called the natural constraint. It says that for all offline vertex J and any subset S of its neighbors, there is an upper bound for the sum of all Xij. This constraint is natural to derive from the Poisson arrival model, since the right-hand side is the probability that at least one online vertex has type in S. So the sum on the left-hand side cannot exceed this probability. Second, despite of the exponentially many constraints, this LP can be solved in polynomial time, since there exists a greedy algorithm to determine the separation oracle. This constraint is also very strong, so it subsumes some LP constraints considered in the previous works. For example, when consider the integral arrival rate case when all the lambda I equals to 1. Previous works uses such constraints that Xij is no more than 2/3, or Xij is no more than 1 minus e to the minus 1, and the sum of two different Xij is no more than 1 minus e to the minus 2. We can verify that the natural constraint contains these two constraints. Since the natural constraint bounds how wide Xij can spread, it leads to an important inequality called the converse of Jensen's inequality. For any convex function f with f0 equal to 0 and any offline vertex j, there is an upper bound for the sum of all lambda I times f xij over lambda I. It also subsumes some previous LP constraints. So this is the natural linear program part. For the algorithm, we extract the meta-algorithm from previous works called the pair sampling. It's a simple algorithm for an online vertex of type I. The algorithm first samples two options j, k from a distribution di related to I. Then, given these two options, the algorithm matches the online vertex to j if j isn't empty and not yet matched. Otherwise, matches to k if k is not empty and not yet matched. So the essential point of this algorithm is the distribution di, which we will carefully construct later. Here, if an online vertex of type I samples jk from di, then we call this online vertex has extended type ijk. Since the type I follows independent Poisson process and the jk is independently sampled. So here, the extended type ijk also follows independent Poisson processes. We consider the matching probability of an offline vertex j. Consider the three cases. First, it's matched by some first option. Second, is by an online vertex with first option empty and second option j. So this vertex simply skips the first option and matches to j. Third, by an online vertex with first option k and second option j, while k is already matched by some other first options. Since all these three cases follows the Poisson processes, we can compute their possibility. And more important, These three cases are independent, so the total probability is 1 minus these three products. Our starting point of the algorithm is the Jallis and Lu's work in 2014, which we call the wasteful correlated sampling. First, compute the xij in the LP, then align subintervals ij of length xij in the big interval of length lambda I. Like in this diagram, there are intervals I1, I2, I3, and the remaining part is I empty. The second step is to sample a point V uniformly at random in this large interval. And V prime is the antipodal point of V. J and K are determined by which intervals V and V prime is in. So this is the algorithm of the wasteful correlated sampling. Using the inequality introduced before, we can give a lower bound of this resampling mass, that is the sum of mu jk over all k different from j. We call that the matching probability consists of these three parts. In the analysis, we amortize the last part to the contribution of j. Then we derive an 0.6995 competitive algorithm. The previous algorithm is called wasteful. It's because if there is a large interval whose xij is greater than half of the lambda I, then V and V prime may lie in the same interval. In order to resolve this problem, we introduce another algorithm called the correlated sampling. In correlated sampling, if there is no such large interval, the algorithm does samely as before. Otherwise, if the first option isn't in this large interval, the second option must lie in this big interval. If the first option is, then we sample the second option, V prime, in other intervals proportionally. So we never consider these large intervals again. In this way, we can make sure that V and V prime do not lie in the same interval. Well, here, we introduce a parameter beta. This beta is greater than 1 and can go to infinity. Then we derive a better lower bound of the resampling mass, hence leading to a 0.711 competitive ratio. This is the unweighted part. For the vertex weighted part, we call that the matching probability consists of these three parts, and we try to amortize the last part to the contribution of j. However, this is impossible in the vertex weighted case since j and k are not of the same weight. On the other hand, we can lower bound the total resampling mass, but not the resampling probability, since the mu j here may be very small, close to 0, leading to this probability close to 0. And we hope to remove this mu j term here. This leads to the algorithmic amortization. In the amortized correlated sampling, we align in the subintervals in the same way as the wasteful sampling. And samples jk in the same way too. However, we add a last step, with a certain probability related to xj, replace the first option j with empty. So we do the amortization in this way. By fine tune the constant beta to 0.299, this algorithm is 0.7009 competitive. At the very last, I will do a brief summary of our work. We proposed two algorithms for the online stochastic matching. The first one is 0.711 competitive in the unweighted case, while the second is 0.7009 in the vertex weighted case. Technically, we first introduced another model called Poisson arrival model. This model is asymptotically equivalent to the online stochastic matching, but introduced a greater level of independence between different online types. And we use the natural linear program with stronger constraints. And in the vertex weighted case, we use algorithmic amortization. That is all of my presentation. Thank you.